Okay, good afternoon. So there are two parts need to be covered in Math 4 that I skipped. One of them has nothing to do with integrals, and that is the topic of asymptotes. And there's another one that you need to know the notion of integrals to calculate some probabilities. I will cover one of them in one session actually. We use one session for each one. So let me close the door first. Okay, so let me motivate you a little bit about the notion of asymptotes. First of all, asymptote is something, not something, is a line, is a straight line that we associate to a function. Okay? And what is the purpose of that? It will help you a little bit to draw a little bit better graph or give a given function sometimes. It's a guiding tool. It's a guiding tool that you can use that to understand the behavior of the function that you are studying a little bit better. Okay, for example, let me just give you a motivating example. For example, let me consider this function f of x equals to e to the power of negative x squared. And then I want you to draw the graph of this function by hand, okay, or at least understand what is the properties of this function. So the first thing that you do is to draw the graph of a function by hand, or sketch, not draw. Sketch the graph of the function by hand. You need to find the local extreme points. Yeah, so these are the main important points in the graph of a function. So I differentiate it. It's the chain rule. It becomes the function itself multiplied by the derivative of the exponent. Then it becomes e to power minus x squared times minus 2x. This is my derivative. And then I put it equal to 0 to find the candidates for local extreme points. So if I do that, this means minus 2x e to power minus x squared is 0. The product of these three numbers is supposed to be 0. Minus 2 is not 0. E to power minus x squared is an exponential. An exponential cannot be equal to 0. So it means that there is only one way to make this product 0, and that is x equals to 0. But x equals to 0 is just a candidate for an extreme point. It might be a max, it might be a mean, or it might be a terrace point. So there are two tests for understanding which one is which. One of them is the first derivative test, drawing the sine table, and then the other one is the second derivative test. You calculate the second derivative again after calculating this, and then you put the number there in the second derivative. If the answer is positive, that is a local minimum. If the answer is negative, that's a local maximum. And if you are unlucky and the second derivative is 0, the test is not conclusive. So you have to do with only the first derivative test. But here my goal is not only doing that. My goal is to draw the graph. So whenever you want to draw the graph, it is better to use the first derivative test and the sine table. So if you remember, the standard sine table was if I have x here, f prime here, and f, the only candidate that I have is 0. If I put 0 to the derivative, of course it becomes 0. If I put 0 into my function, e to power 0 is 1. Then x does not have any limitations here. It goes from minus infinity to infinity. I can assign any value to x, or no limitations there. But then I need to know if f prime is positive or negative. Okay, so this is my f prime. Minus 2 is negative. Exponential is always positive. So far this is negative. If x is positive, the whole combination becomes negative. And if x is negative, the whole combination becomes positive. Of course, you can choose, because this function is continuous, you can choose a random number less than 0 and put it there and understand it. I don't want to repeat all those things. But then you realize here the derivative is positive, so the function is increasing, and then the derivative is negative, the function is decreasing, so you realize that this is a local maximum point. If I want to sketch the graph of this function, you see that this will not give rise to a very good quality graph. Why? Because if you just want to rely on these pieces of information that you see here, yes, you realize that there is one extreme point for my function, and that is a maximum point. The x coordinate is 0, the y coordinate is 1, so it's here. And I know that this should behave like this around that point. Yes, but that's it. If I just want to use this. Okay, so there are a lot of possibilities. You might say that, okay, on the right hand side the function goes down, on the left hand side the function goes up. I mean, so something like this you can draw, imagine. And essentially, if you don't look far away, that's not a bad thing, because based on this information that you have so far locally, this is the graph. It doesn't contradicts what you see on this picture. Yes? But another scenario, but if you draw the graph using GeoGebra, the graph will look like this. Okay? And that is qualitatively completely different from the previous one. So if you want to only rely on the sign table and don't look farther away, there is no difference between this dotted curved line and the blue curved line, because on the right hand side the function decreases. That's true for both of them. On the right hand side the black one goes down, the blue one also goes down all the time. And on the left hand side the function is increasing. It is for both of them. On the left hand side the black curve is increasing, the blue curve is also increasing all the time. So if you just want to constrain yourself within this limit, local point, there is no difference between the dotted line and that one. So this means that would be a good idea if I can find some tool, or I don't know, develop some tools in my hand so that I can immediately use that tool to deviate between these two. To be honest, if the graph is this one, you cannot sell this graph to anyone. Yes, so it's I mean, you might be able if the graph, so these graphs are qualitatively the same, this blue dotted line and this black dotted line, yeah, they are qualitatively the same. But I hope that you agree the black one and this blue one up there are not even qualitatively the same. You will not be able to sell the blue, this black dotted curve for the blue curve. Yes. So the question is that, is there any way that without using GeoGebra we will be able to understand that the real curve of the function is that one, not the black one? Yes.
You can tell the function that we won't go below 0 because it's to the power of.
Yeah, something like that. But still, it doesn't go 0. This behavior that they are getting closer and closer to a straight line is what we call asymptotic behavior. So if I want to understand what is the meaning of asymptote, here, this horizontal line is called an asymptote for this blue curve. What does it mean? It means that if I go far to the ends, either from the right or from the left, the distance, the deviation from my curve to that line becomes smaller and smaller. Here on both ends. Yes? So this is my straight line. These orange lines that I am drawing, they are measuring the deviation of my graph with that line at that particular point. Yes? If the deviation of the graph and a particular line is becoming negligible, then we say that that line is an asymptote for my function. Okay, that's it. Okay, so this line is an asymptote for that function because the deviation between the function and this straight line becomes smaller and smaller, and eventually it becomes negligible if I really go far to the right and far to the left for this case. I don't know, might be I have this scenario, might be I have a graph like this. Yes? Then this straight line that you see here is playing the role of an asymptote, but only on the far right end. Because to the left, the deviation is becoming bigger and bigger when I go to the left. So this cannot play the role of the asymptote of my function on the left part, but it is still playing the role of the asymptote on the right. So this feeling I want you to understand, that is called asymptotic behavior. So, and it doesn't matter if this line is horizontal, vertical, or oblique. But all of them, we need to understand them separately. The details comes from the fact because the horizontal lines, vertical lines, and oblique lines in mathematics have different equations. That is why it makes it a little bit subtle. We have to categorize them into three cases: horizontal ones, vertical ones, and oblique ones. But in all cases, I want you to have a feeling of the asymptotic behavior. For example, if I draw a line like this, an oblique line, and I draw this graph like this, I want you to feel that is also asymptotic behavior, because the deviation between the curve and the straight line is becoming negligible in this case when I go to the far right. So that is the asymptotic behavior. Is that clear? The distance, the deviation from the curve to a straight line becomes negligible either on the far right side or on the far left side, or both. Yes?
But this is assuming that it won't ever cross the line.
No. No, it's getting close, not zero.
Yeah, but like because I mean some curves. I mean you all because I'm assuming you can't draw an asymptote for every curve.
No.
Yeah, so because some curves would just pass through any line that you draw.
No. This is not the case that all the curves have an asymptote. For example, the very famous function y equals to x squared doesn't have any asymptotes.
Yeah.
Yes? Yeah, there's no asymptote for this function. But some functions have asymptotic behaviors. And if there is an asymptotic behavior, discovering and drawing the asymptotes on the coordinate system will help me to guide myself to a better drawing of the curve. Yes? But conceptually, I want you to understand, we categorize the asymptotes into three categories: horizontal, vertical, and oblique, not because the concept is different. Because in the coordinate system, we have three types of lines: horizontal, vertical, and obliques, and the equations of them are different. If I have a horizontal line, passing through P, the equation is y equals to B. If I have a vertical line passing through A, the equation is x equals to A. But if I have an equation, I don't know, in oblique way passes here, the equation is neither this type nor that type, it is kx plus m. So the reason that I want to categorize the asymptotes into three categories is not because the concept is different, because I have three types of equations for three types of lines. But asymptotic behavior means the same. So a straight line is called an asymptote to the graph if the deviation between the graph and that line becomes negligible if I go far to the right or far to the left or both. Yes? But now let us do it one by one together, okay? We want to talk about is what type of functions I can expect to have a horizontal asymptote. For example, this function that you see here, according to this picture, I want to have this feeling that this line is a horizontal asymptote for the blue curve, both on the far right and far left. Okay, but the logic is the other way around. I should be able to give you this function. You yourself need to understand that line is a horizontal asymptote. Okay? So, the first thing I want you to understand is definition. So, definition: horizontal asymptote. Okay, I don't want to write the definition. I want you to tell me what the definition is. So what is, if you want to define a horizontal asymptote, how do you define that? Yes? How should I define a horizontal asymptote? So I would say that the line y equals to b is a horizontal asymptote of the function f of x if what happens? Yes?
If the limit of f of x
Is b when x goes to
infinity.
positive infinity or negative infinity or both?
Yeah.
So if either limit of f of x when x goes to plus infinity is b, or limit of f of x goes to minus infinity is b. And in mathematics, when I say or, always I mean or both. Yes? So this is the simplest possible scenario. So when they ask you to find horizontal asymptotes, that's a different language to say find these limits. Yes? So why this is understandable? Because I told you, when do you expect that a horizontal line becomes an asymptote for your function? So if this is y equals to b, there are four possibilities that this line can serve as a horizontal asymptote for my function. Which possibilities? Either my curve behaves like this, or my curve behaves like that, or my curve behaves like this, or I don't know, my curve behaves like that. So in this case, when I go to the far right, the deviation between that curve and this horizontal line is becoming negligible, even in that case. So in these two cases, I have this is fulfilled. The limit of f of x when x goes to plus infinity is b. But in these two cases, the deviation from this straight line is negligible, either in this case or that case. In these two cases, we say the limit of f of x goes to minus infinity is b. Yes?
So does this mean that like the graph could technically like cross the asymptotes if it approaches zero on, or it approaches b on one end, and then like
Some books say that, so for example, this kind of behavior, this is not asymptotic behavior. You know, some people say that don't consider this as asymptote.
oh yeah, that's
Yes, because that is what you are saying. This is also the deviation from the straight line is becoming simpler and simpler. This is not what we call asymptotic behavior. The asymptotic behavior, if you want to have a precise definition, some books define it that after a while there is no intersection between the graph and the straight line, and the distance becoming small.
but just like the simple case where it's like just like a hump and then it's approaches.
Yeah, that is okay.
That is an
So for example,
asymptote.
so let me say, for example, so like this.
Yeah, something like that.
Yes, this is a horizontal asymptote.
Yeah, and just also
Because
like
according
just
to the definition I told you,
and it's fine that it's only on one end.
yes, yeah.
Yeah.
This. If you have this is a horizontal asymptote for this function, even though I have the crossing point. Okay. So this is the exact way of defining it. But what is the recipe? I give you a function and I ask you to find all horizontal asymptotes. In a indirect way, I am asking to calculate these limits. The reason I am emphasizing on both positive and negative, because there are a lot of examples that the positive value is different from the negative value. But none of these examples you need to be worried about. You don't have them in the book and in the national exam. But technically speaking, when I calculate this one, I am considering the behavior on the right side. I cannot conclude anything from that information about the behavior on the left side. In principle, I have to do two calculations. But as I saw the national exam questions and I saw the book questions, all of them give you the same answers, okay? So let me give you a simple example. So in order to find horizontal asymptotes, the recipe is clear. Take the limit and send x to infinity. If that limit becomes a number, some mistake is that people write b is the asymptote. That's wrong. Asymptote is a line, b is a number. So you have to write y equals to b. If you just write b, you will get 0 points. You have to write y equals to b. Okay, so let me give you some examples, okay? So what is the answer? I calculate the limit of f of x, x goes to plus or minus infinity. But I don't know, do you remember something about calculating these limits? The recipe is the same, but there are some other terms involved here. So for this case, between x squared and 2x, which one will dominate if x is extremely large? X squared. So compared to 2x, compared to x squared, 2x is negligible. That's, by the way, understandable. For example, let us say that x is 1 million. It's a huge number. It's a big number. But its second power, it becomes 10 to power 12, which is a trillion. Yes? So it is 1 million times larger. So of course, it's understandable. And then when you say x goes to infinity, it means your original value is even much greater than 1 million. And then of course, x squared becomes even huger, yes? So I want you to understand that when I want to compare these two, this is negligible with respect to that one. So I can safely get rid of the second term. And here, the same story. So 3x squared, x goes to plus or minus infinity. And then you see that the limit is 1 over 3. But don't write this in the answer sheet. You have to write y, extremely important, equals to 1 over 3. So this is the answer that you have to provide for this problem. Yes? Yes? Okay, so what about this function? Number, for example, 3. Let me write this. F of x equals to sine x over x. What do you think about this one? Hmm?
My thought is that the asymptote for that is
0, yes. But there's a theorem. I don't want to disturb you with those theorems. There's a theorem that if you have a bounded function, which cannot be above a number, a threshold, and below a threshold, and then if you divide it by infinity, the limit becomes 0. Intuitively, it is clear, but rigorously, you need to prove it. But let us try rely on your intuition here. So here I take the limit of f of x when x goes to plus or minus infinity. So then it becomes the limit of sine x over x based on that intuition only. The limit becomes 0. Let me make sure that you are not confusing it with this one. You remember in the topic of derivatives, we had this limit 1, but what was that, do you remember? That was when the case x goes to 0 and it was in radian mode, yes? So don't get disturbed here. So here x goes to plus or minus infinity, so the limit is 0. But don't write y 0, so don't write 0. The answer is y equals to 0. And one more example, we go to the next part. So number 4, if I give you this function, f of x equals to x squared plus 1 just divided by x. What is the horizontal asymptote of this function, if there is any? There are no, yes, here there is no horizontal asymptote, yes. Why? Because if you calculate the limit f of x when x goes to plus or minus infinity, as before, what happens? In the numerator, x squared will dominate, so I ignore x, I ignore 1. But then what happens? It becomes simply x, and x goes to plus or minus infinity. If it is plus infinity, the limit becomes plus infinity. If it is minus infinity, it becomes minus infinity. But the problem is that it does not become a number. If it is not a number, so no horizontal asymptote. Yes? Okay, so what I will do now, we want to go to the other topic, and that is the vertical asymptote. But again, the notion of asymptote is not changed. The concept is the same concept, but I have the vertical line. What do I mean the concept is the same concept? It means that the distance, the deviation from my function to that vertical line is actually becoming negligible. Yes? So, but it is a little bit more tricky. So for example, let me clean this one and then write definition vertical asymptote. Yes. So what is the vertical asymptote? Again, the same idea. For example, let us try to intuit this and then we make it formal. So this vertical line, let us say this point is A. So this line is x equals to A. I say this line is a vertical asymptote if the deviation from my graph to this line becomes negligible. But there are again 4 possibilities, yes? It might be negligible in this manner. You see the distance is becoming smaller and smaller. Or it might be like that, or it might be like this, or I don't know, it might be like that. These are asymptotic behaviors, but occurring on a vertical direction. Okay, but can you tell me, if I want to formalize this behavior, forget about these 3, concentrate on that one, what should I write for it? In terms of limits and things like, I want to symbolize it. How? So this is your function f of x. And then you want to, I don't know, formulate this behavior with mathematical symbols. What do you write? Yes?
Limits as x approaches a or positive a, or a from the positive.
Yes, yes. A from the right.
Yeah.
Yes?
Should be equal to infinity.
Positive. Yes, exactly. So exactly. So this behavior is the limit of f of x. What is happening? You see, when I am here, this, okay, and then distance from my function to this, the deviation is that much. When I get closer, the deviation is smaller. When I get even closer, the deviation becomes smaller. Closer, the deviation is smaller. So it shows that when I get very close to A, the deviation becomes negligible. But I am getting close to A. The symbol that you use to show that you are getting close to A is this symbol. But you want to deviate this behavior from that behavior, from this behavior, from that behavior. So you need to tell me, for example, here, when I get close to A, the distance is also becoming smaller, you see? So if I just write that equals to plus infinity, then I don't know which one I mean, either this one or that one. So to make sure that which one I mean, here I put a plus sign here. So do you remember this plus sign doesn't mean positive A, it means A approached from the right side. So this behavior can be formulated by that. Okay, similarly, what is this one? This is the limit of the function. X becomes closer and closer to A, but from the left side. The left side, you put a negative on top. This doesn't mean negative A. It means A from the left. But the value of the function is still positive infinity. And for these two, similarly, you understand what to write. What should I write for this one? I would write the limit of f of x when x goes to A, but is still from the right-hand side. The value of the function becomes extremely negative number. So it becomes negative infinity. And this one, if you want to understand this behavior, this is the limit of f of x, x goes to A from the left is negative infinity. If at least one of these conditions is met, then we say x equals to A is a vertical asymptote. So I'm a little bit lazy to clean it, and let me just write it like this. So x equals to A, the line, so let me write the vertical line x equals to A is a vertical asymptote of f of x if at least one of the following conditions holds. Yes, and these are the conditions. So this is not as straightforward as the previous case. For finding horizontal asymptotes, the recipe is clear. Take the limit of the function, send x to plus or minus infinity. But here, you have to do some guesswork. The question is that, which number is that? So that when I send x to that number, the limit becomes positive or negative infinity. It's not hard, but I mean, you have to do some guesswork and then prove your guess is correct. Any questions regarding vertical asymptotes? Okay, so let me give you some examples to clarify my point. So the example is this. Determine all vertical asymptotes, if any, so number one. So f of x is 1 over x. This is the simplest possible case probably. So here, you need to ask yourself is there any number, this is the way that you need to think, is there any number so that when I send x to that number, either from left or from right, the answer becomes plus or minus infinity? This is the type of question you need to ask yourself. Okay? Is there any number like a so that when I take the limit of my function and I send x to that number, the answer of that limit becomes either plus infinity or minus infinity? And then I don't think it is hard. Yes, one good candidates for the functions having vertical asymptotes are which type of functions? I mean, very common ones. Fraction functions, yes? Because a fraction is something simple to make it infinity. How you make a fraction infinity? Either by making the numerator infinity or by making the denominator negligible. Yes? Here you cannot do something. Making the numerator infinity is usually not good, because to make the numerator infinity, usually you have to send x to infinity, but infinity is not a number. I need a number. And in this case, that it doesn't even work because the numerator is constant. I cannot tamper with constant. That's constant. So the only thing that I can ask myself, I want to make this fraction to be extremely positively large or negatively large. I have to find this candidate so that when x becomes close to that, it is guaranteed that my function is extremely big. And the only way that I can do it is to make the denominator very small. Because if I make the denominator small, the division becomes extremely large. So, after all these things, how can you summarize this? So what is the candidate? What's a good candidate for the vertical asymptote of this function? 0. Okay, but you have to write x equals to 0. But is it true or false? To guarantee, I mean, the national exam questions are always on that part when I saw them. It's on the part that you need to just write down. So it doesn't matter how you convince yourself. But let us do it properly here. The first thing that you do is your guess, but you have to confirm that your guess works. To confirm that your guess works, you have to justify at least one of these conditions. And of course, in this case, two conditions will work, yes? So for example, to confirm that, I can take the limit and then send x to plus infinity. So what happens? 1 divided by a very small positive number, it becomes a very positive big number. So yes, this works. So this is the vertical asymptote. X equals to 0. But this part is crucial. For example, let me give you another example. If I give you number 2, let me give you this example. F of x equals to x minus 2 over x squared minus 4. So I want you to find all vertical asymptotes for this function. According to what I just told you, and hopefully you realize, there are some candidates here for my vertical asymptote. The candidates are the roots of the denominator. Because if the denominator becomes very small and the numerator is a number, then the division becomes huge. Okay, so the first thing that you do to solve this problem is to find your candidates. The candidates are the roots of the denominator, yes? And then you get two answers. -2, +2. The naive answer is that these are asymptotes. But these are not. One of them is not, yes? Yeah, 2 is not. Why? Because if I calculate the limit of my function and send x to 2 from the left or from the right, let us see. What is this limit? The type of this limit, when you put 2 there, is 0 over 0. Do you remember? 0 over 0 is indeterminate. Yes? So what happens here? I have to get rid of this indeterminacy. So how should I do that? Extremely simple. I factorize it. x goes to 2 from right or from left. But then you see that this one and that one are gone, so this becomes the limit of 1 over x plus 2, x goes to 2 from the right or from the left, but in either case the answer becomes 1 over 4. But I demand to have infinity. You see, in 4 cases, the answer should be infinity, but the answer is not infinity. So this is a fake one. It's not equal to plus or minus infinity, so x equals 2 is not acceptable. It's not a vertical asymptote. But x equals to minus 2 is a vertical asymptote because that's not hard to check. I calculate the limit of my function, x is minus 2 over x squared minus 4, but then I send x to what? Minus 2 from left or right. But here I don't need to factorize. Yes? What is the answer? Because when I put minus 2 up there, it becomes, in a scratch paper, it becomes minus 4. The denominator becomes 0. Minus 4 over 0 is not indeterminate. Yes? By the way, when I write 0, if I write this is impossible. But when I write 0 here, I mean a very small number. I don't mean exactly 0, so I don't want to remind those things again. So then what happens? This becomes infinity. A number divided by 0 is infinity. What type of infinity? If you want, you can determine the type of infinity, but here it doesn't matter because either positive or negative infinity is enough for me. So this means that this is exactly what I want. So there is only one vertical asymptote for this function, and that is x equals to minus 2. I want to give you 2 more examples and then go to the last part. 2 more examples is that, do you think the fraction functions are the only functions with vertical asymptotes or not? Can you guess a function which is not fraction function, but still we have a vertical asymptote for it? This is one question. Another question is that, can you imagine a function with infinitely many vertical asymptotes? You might remember a function from one chapter with having those properties. So I have 2 questions for you. Let us ask you the second one first. Can you imagine a function with infinitely many vertical asymptotes? Yes?
Tangent.
The tangent function, yes? So the tangent function has infinitely many vertical asymptotes. So let me write it number 3. So f of x is equal to tangent x. So tangent x is an invisible fraction. So it is still in that category, because if I want to solve that, I can imagine that this is written as sine over cosine, and then the candidates are the zeros of the denominator. So I put them equal to 0 according to what you learned in trigonometry, yes? So cosine is related to the x-coordinate, so the x-coordinate is 0 here or there. So this x becomes pi over 2 plus n pi, and n belongs to z. So there are infinitely many, and then of course I have to convince myself they are not fake ones. They are not, yes? Because if I send x so that it is close to these 2 points, the numerator is either close to 1 or negative 1, and the denominator is negligible. So the answer is either plus infinity or minus infinity. So they are not fake ones, they are real ones. And there are infinitely many, 1 for each choice of n. So for example, let me write this one and then move on to the next one. So f of x, they might give you 5 tangent of, let us say, x minus pi over 3 plus 7. We want to find vertical asymptotes of this function. Okay, so what can I do? I can say that, okay, f of x is equal to 5 sine x minus pi over 3 plus cosine x minus pi over 3, and then I have a plus 7. So it is also an invisible fraction. The candidates are the zeros of the denominator. Yes? Okay, so what should I do? I put the denominator equal to 0, but then this means that x minus pi over 3 should be pi over 2 plus n pi, but I'm looking for x, so I move pi over 3 to the other side and take the common denominator, so it becomes 5 pi over 6 plus n pi. N belongs to C. There are infinitely many vertical asymptotes for this function as well. Yes? But now the question is still standing. So even though tangent seems not to be a fraction, but indeed it is a fraction. So, but can you imagine of a function which is not fraction at all, but is still we have a vertical asymptote for it? It's a very, very famous function. Yes? Yeah? Yeah, logarithmic functions. Yes, the simplest possible case that I can give you is ln of x itself. I don't want to prove it, but I can try to justify it, okay? So number 5, the function, at least you need to know about this. So f of x equals to ln of x. So what is your claim? If you say that logarithmic function works, do you know what is a vertical asymptote for this function? Ln of x is not fraction at all. It's even not like tangent. Tangent was an invisible fraction. But ln of x is not a fraction, it's just a function. But there is a vertical asymptote for this function. Okay? So I want to test your understanding from graphical point of view because that's also important. Let us test your understanding using GeoGebra. I asked GeoGebra to draw the graph of this one. I just want you to, by looking at the graph, tell me what the asymptote is. So this is GeoGebra. So let me ask GeoGebra to draw the graph. So y equals to ln of x. Okay? Okay, so this is what you get in GeoGebra. Okay, is it enough for you to understand what the equation of the vertical asymptote is? What? Don't say 0. 0 is wrong. Y is x equals to 0. Yes, is that clear? So if I want, I can actually rescale it so that you can see this behavior. Yeah, it cannot calculate it, There is a bug. Yeah, I mean, this is not a bug, of course. This is becoming a very small number, so it cannot deviate. Anyway, so this is by looking at the graph, hopefully you understand that this asymptotic behavior becomes apparent here. Okay, but you might feel that's important. Yes, let me ask you another question. Do you think there is a horizontal asymptote for this function as well? It's a better question. Yes? Yes? So for example, do you think y equals to 2? So let me draw y equals to 2. Okay? It seems that you are still feeling the asymptotic behavior. So is it good to say that y equals to 2 is a horizontal asymptote for this function? That's why I'm saying that feeling is not good in mathematics, so you have to have a rigorous proof for it. But this gives you the wrong impression that this one is the case. But it is not the case, because if I go right to the left, it goes above. Okay, you might say that no, 2 is not good, but let us say 4. No, for some reason, okay, so there are no horizontal asymptotes for this function. I want you to tell me why. That is the previous lesson. Why there is no horizontal asymptote for this function? For horizontal asymptote, what should I do? There is one recipe. To calculate the limit, limit of ln of x, and send x to plus or minus infinity. In this case, minus infinity is not acceptable at all. Why? Because ln of a negative number does not make sense. So I have to live only with one option. But do you, just intuitively, what is ln of a very big number? It is infinite. and infinity is not a number. So there is no horizontal asymptote. But the increase rate of ln is so slow that you get the wrong impression that there is an asymptotic behavior somewhere going on. So ln of x, so if I compare this one, it is good to see that one as well. If I go to home, and then if I draw y equals to x, so y equals to x is actually much, much bigger than ln of x. Okay? So this is interesting to know. ln of x is always below x. But so it means that by looking at the graph, you see that the rate of increase, the function is always increasing. Why the function is always increasing? Let us review things. Why this function is always increasing? Yes?
That's the logarithm of x just means what number to the power of e is x.
Okay, no. A very, very simple answer. That's correct. But a very simple answer. If you want to see a function is increasing or not, you take the derivative. So the derivative of 1 over ln of x is 1 over x. But x should be positive, otherwise ln of x is not defined. If x is positive, 1 over x is also positive. So it means the derivative of ln of x is always positive. So it means the function is always increasing. Okay? But does it mean that if a function, let us test this idea, if the function is always increasing, does it mean that there is no horizontal asymptote? No. Yes, because I can draw a line like this and I can increase my function like this. This function is always increasing. At each step, the amount of increase is smaller and smaller, I agree, but it's always increasing, but still I have a horizontal asymptote. So don't get confused these things. Okay, let us go back to the question. No horizontal asymptotes. Why? Because the limit is infinity, not a number. But everyone hopefully agrees from the graph that x equals to 0 is the vertical asymptote. How can you prove this? Justify it, not prove, because rigorously it's a little bit hard for you. So I need to convince myself that let me write it with blue. I need to convince myself that the limit of this function, if x goes to 0 from the right or from the left, it becomes either plus or minus infinity. This is in a scratch paper. I ask myself, is one of them true or not? I immediately understand that I am not allowed to send x to 0 from the left, because if x is negative, ln is not defined. So get rid of that. And from this picture, you know which one should be true. So which one should be true? So you see, when you go to the right, yes. So you see, when I go to 0 from the right-hand side, the branch of my function goes to hell. Yes? It goes to negative infinity. So this means that this should be negative infinity. Yes? But can you justify this a little bit more rigorously? Because this is a scratch work paper, yes? It is good to know this limit. Mathematicians can prove this rigorously, but this is intuitively enough. So this means that I want to convince myself this is approximately, so I want to prove this. If x is very small, ln of x is very negative. And this is not hard to convince yourself about. Yes? Why is that? Okay, so let me call ln of x to be y. From this, I can say e to power y is x. Yes? So x is very small. So you are supposed to make x, the output, very small. What do you choose for y? If you want to make x small, you cannot choose positive values for y, because choosing bigger positive values for y increases the value of x. But if I choose very negative values for y, I am making x smaller, because e to the power of minus infinity can be viewed as e to the power of infinity, and it becomes 0. Yes? So remember, this function has one vertical asymptote, and that is x equals to 0. And one question, then we go to the next topic. If I give you this function, 5 logarithm of 5x minus 2 to the base 3 plus 7. Is there a vertical asymptote for this function? What do you think about this? Is there any vertical asymptote for that function? That's also a logarithmic function. So remember, logarithmic functions, I cannot say the only functions that I remember now, they are not fractional functions, but still they have a vertical asymptote. So can you tell me what is the vertical asymptote for this logarithmic function? So the one that makes the argument 0. So for this one, you have to put this equal to 0. And x becomes 2 over 5. So that's the vertical asymptote for this logarithmic function. I would say these are optionals. I haven't seen any questions in the book or in the national exam using this. But I just want you to give the feeling that it might happen that there is a non-fraction function which has a vertical asymptote. Okay, so what do you think about oblique asymptotes? These are more technical ones. Vertical asymptotes. Sorry, oblique asymptotes. So let me clean this. I don't want to, of course I can define it again. So if you want to define it, it's a good exercise to do this. Oblique. So you understand that the asymptotic behavior. So if I have this coordinate system, and let me draw this oblique line, let me call it y equals to kx plus m. It's an oblique line. When you say that this is an asymptote for your function, what kind of behavior you expect around this line? The same asymptotic behavior, yes? So it means that this is the case that this might happen on the far right, or this might happen on the far right, or this might happen on the far left, or this might happen on the far left. These are the cases. So how do you formalize this? For example, let us concentrate on this branch. The problem is that the deviation is shrinking if I want to expect an asymptotic behavior. But that is easy. Can you tell me what is this deviation? How this deviation is formalized? What is the length of here? How can I formalize the length? It's easy. So from here to here is how much? If this is x, this is f of x. This red one is my function. What is this length? Kx plus m. So this length becomes the difference between these two heights. So it becomes f of x minus k of x plus m in total. But this is for the case that the graph is above this one. Yes? But for this case, I have to write this one first, this one second. To not worry about that, I put an absolute value. So it is the distance, this is the deviation, the magnitude of the deviation of my function from that line. I expect this to be what? 0. Yes? Limit of x goes to plus infinity is 0. This is for these two cases. For these two cases, what can I write? The similar argument gives me this. So if I want to, at the level of definition, I can write this. I can say the oblique line, the line y equals to kx plus m is an oblique asymptote of of f of x if either number 1 or number 2. I don't want you to memorize them. I want you to see that I am following the same logic all the way around, and that is the deviation from my function to that line shrinks to 0 on extreme cases. There is a formula in your book, but it is not in the formula sheet, yes?
Was it do we need the absolute value? Like, shouldn't the limit work just as well?
No, because my logic, yes, you are right. You can take the absolute value because there is a theorem that if the limit of absolute value is 0, the limit of absolute value of a function is 0 if and only if the limit of the function is 0. But because I tried, if you don't like, just put pair of brackets. But because I talked about distance, give the motivation, I put the absolute value. But you are completely right. You can take it and put this. Okay, but the problem is that this is a good definition, but it is not very useful. It is useful. I want to make a useful idea from it, because there is a formula in the book. None of these formulas are in the formula sheet. Okay, so then there is a theorem that the book has mentioned it, but I think that is not the most useful one if you want to use it. Okay, so the formulas, I will write it for you. Okay, so if you want to find this line, there are two unknowns for you, k and m. The formula for k is proven to be the limit of f of x over x, x goes to plus or minus infinity, and m is the limit of f of x minus kx when x goes to plus or minus infinity. Yeah, it needs a little bit of work to prove them. I saw one example using the formulas. I am not proving the formula now. We can discuss about that if you like, but I want to finalize the asymptote today. So let me give you an example so that we can use this formula to derive the oblique asymptote. But as I told you, even though they are in the book, they are not in the formula sheet. And I don't recommend to use them because there is a simpler way to do it. But let me give you a function, and I want you to find, using these formulas, oblique asymptote. So the function is this: f of x, x squared plus x plus 1 over x. I want to find oblique asymptotes for this function if there is any one. These are very straightforward because there is a formula for k, and be careful, you have to calculate k first, because for calculating m, you need the value of k. Okay, so what you do, you write the formula, k is equal to the limit of your function f of x, x squared plus x plus 1 over x, this is your function, divided by x, x goes to plus or minus infinity. Your duty is to calculate this limit. If there is a number coming out, then k is that number. If the answer is infinity, there are no there is no oblique asymptote. But how can I calculate this? I give a denominator 1 here, so 1 times that, x times this, so this becomes limit of x squared plus x plus 1 divided x times that is x squared, and x goes to plus or minus infinity. And then of course the same trick, between these three, x squared dominates, and x squared is the only term in the denominator. So this becomes just simply 1. It doesn't matter if it is plus infinity or minus infinity, the answer is 1. So k value is 1 in this problem. I haven't justified why the formulas work. I have just defined this formula. Now I have just defined for you what is the meaning of an oblique asymptote. By the way, it's not hard to see. You see, if I divide everything by x, what happens? Because that's the definition. If I divide everything by x, so this becomes limit of f of x over x minus k plus m over x. X goes to infinity, yes? This is a constant divided by x, the limit is 0. And the answer to the limit should be 0. So it means k should be the limit of this part. It's intuitively, yes? And then if you know k and you are looking for m, because m is a constant, you can just move m outside. It becomes f of x minus k of x is equal to minus m. Yes? So that's the proof. Okay? But I don't recommend using this formula, but this is the only example I will solve using this formula. After you found k, this is a little bit tricky, so you need to know the limits a little bit good, you know. M becomes equal to the limit, x goes to plus or minus infinity, and then I have my function, which is x squared plus x plus 1 over x minus kx, but I found k is 1, so it becomes just simply minus x. One thing that is important to understand is that if you are not good in limits, you might say that, what is the limit, by the way? Let me ask you. So that's why I'm saying that you have to do it properly. The reason is that might be you get 0. I did the same mistake with Natur students because I wanted to put everything under the rug. It didn't work, okay? And then I was in trouble. So one idea is that I want to use the same idea. Yes, what is that?
It's the limit 1.
The limit is 1, not 0. Because if you follow this, you might say that x squared dominates x, dominates 1. So let me ignore x and 1. Then it becomes x squared over x, which is x minus x becomes 0. That's the mistake that I made because I wanted to do it very fast, but it didn't work, yes. The reason why this idea is not correct, the reason is that not only 0 over 0 is indeterminate, infinity minus infinity is also indeterminate. We cannot say infinity minus infinity is 0. The limit of this part is infinity. The limit of this part is also infinity, so it's infinity minus infinity. That is the reason that naive argument does not work. Okay, so we have to do it properly. Then there are different ways to do it properly. If you want, you can take the common denominator or separate them. Yes? So what happens? This becomes the limit x squared over x over x, 1 over x, and then I have minus x at the end. Now you see this is not infinity minus infinity, it is infinity minus infinity, but whatever infinity is this one, that is the same size infinity, they are gone. And then 1 over x, x goes to infinity is 0, 1 is left, so m is 1. So what happens? M is 1. And then the asymptote that you are supposed to write is kx plus m, but both of them are 1, so it becomes x plus 1. So this is the correct oblique asymptote. I will solve this problem using a different idea, and I want you to learn that one. Probably that one is better. But I just wanted to show you that the formula, which is not hard to derive, hopefully you understood what I said, using that formula you can find the oblique asymptote. Okay? But what is the other way? The other way around this problem is this idea that I want you to learn this, because majority of the problems I saw, all of them can be solved using this idea.
Did you say that these formulas for K and M were not informations?
No, they are not. I checked it because I was not sure, but I checked it.
Yeah, that's something we should want them. Or is it?
If you want to use it, which I don't recommend,
Okay.
because I want to tell you something else. Uh, so if I want to do it the other way around, can you tell me how? You know, my question is this. So if you say y equals to kx plus m is an oblique asymptote here, what do you expect? If you understood the notion of this, you don't need to memorize it, because whenever you think, it comes to your mind immediately. So let me ask you again. When I say this line is an asymptote to this, what do I mean?
Comes very close to f of x.
Yes, so it means, let us use the word deviation. I mean, you will remind it. So it means that this function deviates from that negligibly. I don't know if that's the correct word or not. I mean, infinitesimal, yes? So you would say that if this is supposed to be an oblique asymptote of this, this function should deviate from that line a little bit. Deviate from that line means it is equal to that line plus a deviation, but this deviation becomes negligible if x becomes large. Yes? That is, if you think a little bit deeper, that's exactly the meaning of asymptote, no matter which type of asymptote you're talking. So, f of x, let us say I ask you to analyze the general form of a function whose oblique asymptote is this. So it means that function should be a deviation from this line, and the deviation becomes negligible if I go far to the right or far to the end. So what does it mean? It means f of x should be that function plus a deviation. The deviation goes to 0 when x is plus or minus infinity. I would recommend you to learn this. This is better. For example, let us go back to this function and try to find the oblique asymptote using this idea. So what can I do now? F of x is equal to x squared plus x plus 1 over x. The only thing you have to have in mind is to write your function in this form, because if it is not possible to write it in this form, give it up. There is no oblique asymptote. If there is supposed to be an oblique asymptote, it should be of this form. So can you write this in a way that it becomes a line plus a deviation? Extremely simple. What's that? Write this function as a line, straight line, plus a deviation. What is that line? It's off the board. Yeah, it's x plus 1 over x. Yes? Is that right? X squared over x over x, 1 over x. And now look, this function is a line plus a deviation. But that deviation is important. That deviation goes to limits of 1 over x when x goes to plus or minus infinity is equal to what? 0. That's it. So y equals to x plus 1 is your oblique asymptote. This is the best way to find it.
But this, I mean, this.
Yeah, of course, then of course you have to be creative to be able to decompose your function to a line and a deviation. But most of the questions in the book and the national exam are extremely easy to do that. Otherwise, then you have to do it. There's no other way, of course.
And can you do this in every case?
Yeah, no, you can't. This is a proof. I mean, the formulas can be proven everywhere.
Because if you have some other strange function where it's like not obvious.
No, if that's not obvious, of course I am in trouble. Yes,
Yeah,
you're right.
yeah.
Then I have to do this.
Yeah.
But the questions in the book and in the national exam, you can always do them. It's not hard. But the concept is important, okay? And by the way, let me predict what happens. I can use GeoGebra to draw the graph of this one, but let me ask your opinion about that. One question, do you think a function can have a horizontal, can a function have a horizontal and vertical simultaneously?
Yeah. 1 over x is.
Yeah, 1 over x is the one that this one is vertical, horizontal, this one is vertical. But that's possible. If you draw this graph, it becomes like this. So this is a function who has a horizontal and a vertical simultaneously. Do you think a function can have vertical and oblique? Exactly this function. Yes? This function has an oblique. What is the vertical one? Do you remember? The vertical one means the value for x, the candidate is the root of the denominator. Yes? So this is the oblique one. Is there any vertical one for this? If you go back to the lesson of the vertical one, the candidates are the roots of the denominator. So x equals to 0. Is it acceptable? How should I know it's acceptable or not? I have to make x very close to this number to see if the function blows up or blows down, okay? So is that the case? Yes. If x is very small, the numerator becomes close to 1, the denominator becomes extremely small. 1 divided by extremely small is extremely big. So x equals to 0 is a vertical asymptote. So a vertical asymptote and a what? Oblique asymptote. Now my question, do you think we can have oblique? So how did we test? Vertical, horizontal is possible. Oblique, vertical is possible. What is the other scenario? Horizontal and oblique. Do you think horizontal and oblique, we can have them together? We cannot. Why? Yes?
Because if we think about it, if an horizontal line exists, then it basically becomes a straight horizontal line, and then oblique, it has to somehow go along with it.
This is one way to understand it. But another way is that oblique, horizontal is a special case of oblique. Yes? Vertical is not a special case of oblique.
Oh,
Because for vertical ones, I do not have any slope. Okay? But if I have a vertical, it means if I have a horizontal, k becomes 0. Yes? So we cannot have horizontal and oblique together. Or in other words, when I say horizontal, it is automatically oblique, in which k value is 0. Yes? That's also one way to look at it. Yes?
But like the graph that is like completely flat and then curves up at some point and then just like,
Okay, yes. In that case, you are right. Yes, and let me, so what you are saying is this. No, but okay. No, I have to correct my question. Thank you. Because they are happening on two different branches. So this is horizontal. You are right. So what you are saying is that very good. So you are saying this. Yes. But yes, you are right. I have to be careful. Because this happens on the right side branch. This happens on the left side branch. This cannot happen simultaneously. Yes, but that's correct. I think we can have it. Can I find a function for it? No, but in principle this is possible. You are right. I should know the function as well. Yeah, this by the way, this is not something strange. Yes? Because you are right. Because what you are looking here, for this one to be oblique, so it means that this okay, the reason we put plus or minus, because you don't have these functions. It is possible that for positive infinity I have a number, but for negative infinity I have 0. This can happen. Okay? So then it means that on the negative infinity branch I have horizontal, on the positive infinity branch I have oblique. Yes, this can happen. Thank you. Okay. Any questions here? Is that understandable? So this is the topic of asymptotes. But let me give you a little bit harder. I haven't seen that question, but let me, because Oscar asked me a question, if we cannot engineer that. I don't know. I don't want to tell you, but I want to see if you can discover it. For example, what do you think about this? Yes. What?
No.
Time is finished? No. What is that?
Sorry?
What did you say?
No, I didn't have.
Okay. So let me write one function. F of x equals to, let me write it like this. 3x squared plus 5x. Now let me make it cubed, and let me make it 2 minus 2x plus 1, and then I would write it as x squared plus 1. Okay. If I give you this function, I haven't seen this question at this level, but if I give you this and I ask you to find the oblique asymptote, first of all, do you think there might be an oblique asymptote for this? No, you can immediately realize it because I erased the formula. Do you remember for the formula for k was f of x divided by x? When I divide by x, it means the power of x becomes x cubed. And if this is x cubed, the numerator is also x cubed, the final answer becomes a number. Yes? Because if I have two polynomials, so can you tell me what is the limit of this function when x goes to infinity right away without any changes? The limit of this function. Here 2x cubed will dominate. Here x squared will dominate. When I simplify, x is left in the numerator. So the limit becomes infinity. If it was the other way around, if it was 2 and this is 3, then 2 will dominate, 3 will dominate, but the x will remain in the denominator, so the limit becomes 0, 1 over. Okay, so now here you should expect that if the degrees differ exactly by 1, there is an oblique asymptote. This is a rule of thumb. But how can I find that? Either you have to have that formula in your memory and then suffer a little bit to calculate those two limits, or you have to engineer it in a way that this will work. Writing it as a function, writing it as a line plus a deviation and confirm that the deviation goes to 0. Yes, exactly. Well, that was the point. So the systematic way is to do the long division if you cannot engineer that. If you are smart, of course, you don't need the tricks. If you are not smart, you have to suffer. So there is no other way. If you know, let me know. So this one is, you have to calculate this long division. But how do you think long division will help? Because long division was useful for the cases we want to factorize. Here we do not want to factorize, but this will help. So I will divide this by that one. So let me do it quickly. So it becomes 2x. And then I multiply there, change the signs. And then I add them up. Agree? But I have to continue one more. And then it becomes minus 9x plus 1. Do you agree with my calculations? Check them out if I haven't done something wrong. Okay, did you check my calculations? Is that right? So I took this numerator and used the long division divided by that. So 2x, yeah, that's correct. And then I add them, this one goes with that one, minus 4x.
It should be minus 5. It should be just minus 5, right? Not minus 5x.
What?
The last step.
Ah, yes, thank you. This is what? Minus 5, you are right. So what happens then? So it becomes minus 4x, minus 4. And can I continue division? No, because the degree is less than that degree. But what can I write? I can write 2x cubed plus 5x squared minus 2x plus 1 is equal to what? This multiplied by that plus this. Yes? Yes? And now my original function is this one divided by that. So I divide. But on the right hand side I have two things to divide. Yes? And then what happens? This one and that one are gone. It becomes 2x plus 5, and then minus 4x plus 4 over x squared plus 1. Yes? So my function is a line plus a deviation. Is that deviation goes to 0? Does this deviation go to 0? Yes. Why? Because the degree of the denominator is x squared, the degree of this one is 1. So in the numerator 4x dominates, in the denominator x squared dominates. So it means that it becomes 4 over x, x goes to infinity, it becomes 0. So then it means that, yes, this is my oblique asymptote. But not that one, of course. I have to write y equals to 2x plus 5. I haven't seen this type of questions in the national exam or anything. But remember, if you have a polynomial function divided by a polynomial function in which the degree of the numerator is exactly 1 unit more, it is guaranteed that you have an oblique asymptote. If you can engineer it using this simple trick, do it. Otherwise, long division will help you to do that. Okay, I know you are tired, but don't worry, we continue because we have to finish this lesson. So let us solve some problems from the national exam. Can you see this question? Yes, a curve is given by that equation. Draw the asymptotes. It's a national exam question, the last one that is exposed, 2022. I don't know what happened in Sweden. They have exposed 2022. It should be remain confidential for 10 years. Yeah, that's what I'm saying. And then there are 2 points for you there. So don't lose it. Because let me make the question bigger. You don't need, of course, they have mentioned what? A curve is given by this function. Draw the asymptotes of the curve in the coordinate system. Yes?
Wait, so we're not actually supposed to see this?
No, you are supposed.
Oh.
I don't want to put myself in the jail. That's what I'm saying. I don't know what happened. They exposed this question, even though it's not from 10 years back. It is on, yeah, you can find it on the Skolverket. Because the policy was to expose the question for after 10 years. But as you see, it is 2022.
Why did I have that rule?
Yeah, from my perspective, laziness. It's a simple explanation, yes? Because they want to use these questions over and over again. Yeah. Yeah.
Could you link it on Google Classroom?
Yeah, I have already put them long back, 3 months ago, 4 months ago, under the tab of Google Classwork. Yeah, sorry, Classwork. Okay, anyway, let us do this one because the time is running. What do you think is the possible asymptotes for this function? Yes? By this lesson that I just told you, the oblique one is the simplest possible one. What is the oblique one? This function is a deviation from a line. This is your line, and this is its deviation. But does the deviation go to 0 when x becomes large? Yes. So finished. Y equals to x minus 1 is your oblique asymptote. And of course, the only thing that you have to do is to draw it on the grid paper. I'm assuming that you haven't forgotten your Math 1C then. So that drawing is up to you. But is there any other asymptote for this function? Is there any horizontal asymptote for this function? For horizontal, you send x to infinity. If you send x to infinity, this part vanishes, but this part becomes infinity. So there is no number, so no horizontal asymptote. Is there any vertical asymptote? For vertical asymptote, the candidates are the zeros of the denominators. There's only one denominator here. The candidate is x equals to minus 2. Is it correct or not? You can convince yourself. Take the limit, send x to minus 2. It becomes infinity. So yes, x equals to minus 2 is another one. That's it. 2 points for nothing. Yes? Yeah. By the way, it's not that hard. When I don't know, I had this impression. I got this impression from you that the national exam is hard. But when I started solving the problems, I see that the problems are very simple, by the way. There are some hard ones there. But still, if you lose 13 points out of 60, you still don't lose the chance even getting an A. So in principle, you can get rid of 20% of the questions, but still you can get an A. Okay? So yes, I have to take my words back. That's not hard at all. Okay? Yes. Yeah, because I got this hardness impression from students every time I see that when I cut the papers, there are strange things going on. Yes? And even though the passing threshold is 15 out of 60, I see blank papers. So yeah, be fair a little bit to your teacher. Yes, don't leave it blank. Write something there. Okay. Yes.
So, like looking through old national tests, it feels like they take the problems from the book. Like they kind of are similar to the book, no?
They are not exactly that, but of course I agree with you. They are not a different topic.
Yeah, like
The book has design. I mean, the people who are designing national exams are probably some authors of these books.
yeah.
So in principle, they have the same mindset when they want to design. Yes.
I think Simon checks we only have one more math 4 lesson before the national exam. Do you know if it's possible to arrange an additional lesson or something?
The problem is that yes, unfortunately, next week is also a holiday. I wanted to ask Morten to give that lesson to me. I don't know why we have so many holidays this year. Is it common? Yeah, if this is related to Jesus, it happens every year. Yes, it should happen, but I don't have the memory for it. I will try to do it. Might be, and then the problem is that let me not record all these